Great.
The dates that you're here listed.
Well, sorry, I was last couple of days. Okay, with crazy. I did actually.
Okay.
So I mean, I saw the reply, but I didn't put the dates. But
I think,
the problem is that I don't know my own dates.
okay, fair enough.
So
I think he said January 21st and February 18th.
it's actually that for me, I'm definitely away on February 18th.
Okay.
That's 100%. And
Okay.
January 21st. Actually, you know what? Yeah, actually, both dates.
Can I? Or
He suggested, but I
Would not have been if other dates will work for him.
Yeah, because January 21st is my mother's birthday. And,
yeah.
February 18th. That's the week that I actually, you know what? Actually, you know what?
So all the white chalks are short and broken. Yeah, I guess we'll try. We'll just switch if around. Oh, are you sure? I don't want to break your nice talk. No, I'll start with the short one. Thanks.
So we're very happy to have Wenjun today, who's going to tell us about spectral R-matrices and affine Grassmannians, equivariant affine Grassmannians.
Thank you very much for inviting me here. I'm happy to be here to give the talk. So yeah, I'll explain my joint work with Rashid Abedin, where we defined some analog of Yangian algebras for not reductive, but for solvable Lie algebras using geometry of equivariant affine Grassmannian. And the motivation was actually from holomorphic topological field theory. So I think we have 2 hours, and in the first hour, I'll start by kind of explaining in a very heuristic way, meaning very non-rigorous way, what we expect from defects in 4-dimensional holomorphic topological theory, and then I will jump to kind of the theories that we study, which is holomorphic topological twist of 4D and 2 theories. So first part, titled Defects in 4-dimensional holomorphic topological theories. So what we're interested in is so-called holomorphic topological field theories. So there are some generalizations of what we know well called TQFTs. So let me start with reminding you what we know about TQFTs. Well, one of the nice results in TQFTs is that defects in TQFTs organize themselves into algebras and higher categories, and so there's a lot of tools in how algebra dealing with these TQFTs. So if I have a d-dimensional TQFT, then I can ask for all the k-dimensional defects or k-dimensional observables. And it is well known that these kind of observables organize themselves into a really nice object called ED minus K category. Roughly speaking, ED minus K is telling you that the codimension of this thing is D minus K. There's D minus K dimensions where you can collide these observables. And it's a K category because I can take harms in K different directions. So, and moreover, for a really nice kind of fully extended TQFT, we have this result of cobordism hypothesis. Which I think is proven in full generality by Lurie, which says that basically everything you want to know about this TQFT is encoded by a single thing, which is what it assigns to a point, which is a orientable, fully orientable D-1 category. So basically what this says is that once you know what it assigns to this, then you can use cutting gluing to reconstruct all the higher defects. So it's a very powerful result. It tells sort of classifies TQFTs. And physically, the objects in this thing are boundary conditions, and which is why they have a D-1 category structure. Another kind of well-known example is in the case when my dimension, space-time dimension is 3, and I'm looking at one-dimensional defect, namely I'm looking at line defects. It's well known that this thing is going to form a E2-1 category, and then a less fancy way to say that it's a braided tensor category. And then again, like turns out that in many cases, in the very dualizable cases, knowing this braided tensor category is enough to know, for example, state spaces and partition functions via the Witten-Rest chicken 2RF construction. Just say that basically studying defects in TQFTs is very fruitful. It organizes itself in a very nice higher algebra structure and tells you a lot about the physics. And the kind of thing we would like to do is to ask whether we can generalize any of the above to not fully TQFTs, to what I call holomorphic topological field theories. And I won't consider a full any general HT theory. I would consider theories defined on C times RD, and mostly I will focus on D is 1 and 2. So roughly speaking, these are quantum field theories that will depend on sort of on the complex structure of C and only on the topology of RD. So anything you want to compute will turn out to be like holomorphic dependent here and topologically dependent here. And in this, so the manifold should, the space-time manifold locally look like this. And in general, you need a so-called transverse holomorphic foliation to define a gauge theory, HT theory. So the kind of question, and we would like to try to illustrate in pictures is what algebraic structures control defects in these theories. In a sense of that, in the sense of like some kind of category with some nice structures or some kind of algebra with some higher structures. And for concreteness and for simplicity, and I only
assign some kind of category treatment of some kind of category 1, category 2, category so on for some kind of manifold or something
right.
Here instead of
Yeah.
Instead of your total full space time is this, but then you're going to assign category to what?
So I will go over some examples. Again, like this is there's I at least personally am not aware of a full definition of what an HTQFT is in the full categorical sense. So again, as I said, I'm only going to focus on dimension 1 and 2. And you might ask, why do you care about this these HT theories? And the first answer, I guess, give you 3 quick answers. Is first one is it kind of nicely combines conformal field theory data with topological quantum field theory data. So it combines, maybe you like chiral structures, which is conformal data, with sort of algebra structures, which is the topological data. So they create some nice interaction. And this interaction is actually what turns out to be important for this work. And moreover, because I have this complex dependence, I can look at state spaces associated to curves. And these state spaces will tell me something about geometry of complex curves. Yeah. Complex curve dimension 1. And we already know this from, for example, the book of Franco Benzvi. Conformal blocks tell you geometry. They give you D modules on curves. And finally, many of the interesting TQFTs that we care about actually can come from deformation of holomorphic topological series. So you can start with an HT theory and do some deformation to get TQFT. So one of the examples of such is A and B twist of 3D into 4 theories. There's a half twist in the theories and gives you the holomorphic topological theory. And
the point here is that just one holomorphic topological twist, so such that they can deform both
in both and B, yeah. And then in fact, it's expected that a mirror symmetry should be a statement also about the holomorphic topological theories. And in particular, there's actually some A and B twists of TQFTs that only admits a Lagrangian description in the HT theory, especially those of rank 0. So kind of studying HT theories is the fun place that connects to all of them. Okay, so Sasha asked me about what exactly I'm trying to assign. So I'm going to start with considering some examples. Number 2. I would like to first look at local defects or local operators in an HT. Okay. Let's look at first generally C times RD. I'm asking for observables that support at a point on this space-time. So let's specify a point. And I'll just say that this A, curly A, is this set of observables. Now, let's assume that in locally everything's translation invariant. So this A kind of labels the local observables everywhere. So then,
observable exceeding the point. So in terms of just topological, that would be what?
That'd be what you assign to a D-1 dimensional sphere.
That's what this T-1 dimensional. So that thing is it's a vector.
It's a vector space. It's an algebra, right? It's an algebra because their sphere have all these different gluings. Yeah, but it's a vector. Yeah, it's a vector space. It's a vector space, but it has a lot of structures. For example, you can fix Z, then you can let X collide, right? So then, in particular, because you have D dimensions, you can collide. For each Z, you should get an ED algebra. And moreover, you can fix X. Then you can let Z vary. And when you vary Z, you expect to have a chiral or vertex algebra. And suppose I don't have C, I just have a C being R2, then this chiral algebra will become the E2 algebra. And then you know that there is some nice, to define really observables in this theory, you need to specify some compatibility conditions, which is roughly what dot additivity is about. So here you also need some compatibility. But I don't know what that is.
ET algebra in the category of Bernoulli's algebras.
I think that's the.
Yes, that's what it is.
That's what it sort of should be, but I think the problem is that there are some higher structures that at least I don't understand how to capture. Maybe y'all can help me with this. Let's take an example. Let's say D is just 1. Then ED algebra is just an algebra. So I just have an algebra. And I have a chiral algebra. So namely, the spectral space has a multiplication, which I'll denote by star, and the intertwining operator, which I denote by y. Right. So the compatibility condition should somehow be stated that these two things are compatible, that they're commutative. And then if you take that naively, you write a formula that look like this, that for every A, B, C, D inside of A, the following is true. Right. So this is just saying that multiplication is a map of vertex algebras. But if you take this too seriously, too literally, so if we take this literally, then we can deduce that A star is a commutative algebra, and moreover, y is just e to the zt A star B.
Just saying the following fact, which is well known, which is that you have an E1 algebra in vertex algebra, so not derived vertex algebra, but ordinary vertex algebra. That's the same thing as a commutative.
Yes.
So this
Yes. Yes. Yeah, exactly.
Unexpected statement.
Right. Yeah. So, right, exactly. So I guess I'm just let me just write it down. The argument is, of course, you can. And then you can if you then use this distribution, you find that this is B times e to the zta. So in particular, you in order to get anything interesting, you have to kind of keep track of a homotopy. And maybe you know, but I just actually have never seen this the complete homotopy being written down. So let me say that there must be higher structures, which I have no idea what they are. But I have a bunch of examples. So if you already know what the higher structure should be, maybe we can go through these examples to see if anything could make sense. And the examples will come. I mean, these examples are well known, but they also arise as HT theories. But so I want to say that this equality will be important later when I sort of will categorify this equality, these equalities by replacing elements in an algebra by elements in objects in a category. Okay, so although I don't know what the higher structure should be, physics actually tell us what the cohomology should have, what structure the cohomology should have. So this is the work of Oyagi, and also sort of Dimofte, Bensby, Knightsky, which tells us that the cohomology carries some higher brackets that come from like an integration over of descendants over cycles. That's some words in physics. But roughly speaking, in this context, this cohomology of A will always be a commutative algebra, as we have shown here. But it will has another interesting structure. It will have a one-shifted lambda bracket. In other words, usually what we write is like this. So this is a one-shifted Poisson structure on the space that's sort of dependent upon the formal variable lambda. And I think now recently it was given another name of ravioli vertex algebras by Garner and Williams. I actually don't know how useful this language is, but like at the end of the day, this algebra is a commutative algebra with a one-shifted lambda bracket. So whatever this higher structure is, it should be a quantization of this classical one-shifted lambda Poisson structure. And as far as I understand, I don't think we really know what that is, unless Nick will tell me otherwise. Yes. Okay. And can you somehow get a lambda bracket out? Just like how if you have a E3 algebra, you should get a two-shifted Poisson structure.
Yeah, I think that should be fine.
No.
Well,
Okay, yeah. I would love to know about it. So I said I will give you some examples, but the examples that will actually come will follow from sort of considering a higher set of some higher dimensional defects. In particular, I will now focus on line defects in HT theories. In the flavor of what I have been doing so far, I will again only focus on specific small dimensions. So here I'm considering a homological theory on C times R, and I'm looking for line defects which sit at a point. Now only sit at a point in C, and then they stretch along R, and I call this category L, let's say. So what structure should L have? Well, first of all, because you have a topological dimension, observables defects along this topological dimension will always form a category. So L is a category. And moreover, you should be able to put L at different points on C, and therefore L should have L should be a unital chiral category. Or maybe Jan Sobelman has another definition called meromorphic tensor category. I don't know what's the relation between these two, but both of them are sort of valid from a physics perspective. So here it's saying that you can put two line operators together. When they are close to each other, you should be able to ask what's the effective line operator.
Just a monomorphic diagram, such that the meromorphic is only the braid. It's only the braid.
No, that's a braided meromorphic category.
So all the monoidal structures all this structure.
Not necessarily. I think it's not necessarily just monoidal. So you could have meromorphic tensor category that literally only depend on, that only have one kind of monoidal structure.
A typical example of kind of synchronization is something like nine-dimensional representations with one algebras.
Yeah, well, the reason that has a monoidal structure is that there you have actual dimensions here. The quantum field theory actually have other topological dimensions. In the case of C times R, this would just be that. Well, either way, like this is more well known and people study this well. And in particular, if you have one of these guys, then you can get an example of a E1 chiral algebra. Because what is that? That is just local operator in such a quantum field theory. And you should be able to compute local operator as junctions of a unit object in this category. So if I take A to be the endomorphism of 1 inside L, then this should be a E1 chiral algebra. Should be E1 chiral algebra. And in particular, if you have such an L, you should be able to take one of this, take its cohomology, and find that you have a bracket coming from a descendant of a circle. Let me give you an explicit example that's kind of already well known. L, let's take L to be the affine representation of affine Kac-Moody at level K. This is a chiral category. One is the vacuum module. In this case, I can compute this derived endomorphism. And we know the answer. The answer is that this is by definition the center of the affine Kac-Moody algebra. And the center is zero in most cases, except at critical level. And at critical level, we have the so-called Fagan-Frankel duality. Of course, at a critical level, which tells you that this thing looks like functions on the uppers for the Langlands dual group. This is sort of a Langlands duality, and kind of an important story for the Bayes and Drinfeld's idea for geometric Langlands. Great. So, however, when you write this equality, you can already take cohomology. So, I will write a chain level model that kind of manifests this pairing explicitly. It's given by the following. So, I'm compute derived endomorphism of modules for the affine Kac-Moody algebra. Well, I can use a junction because identity is an induced module, so it's the same as geo homomorphism from C to the affine Kac-Moody algebra, or it's just the geo invariance. And when I compute geo invariance, one of the chain model I can use is to use the Chevalier-Eilenberg complex. And as a vector space, this is symmetric algebra of T inverse GT inverse, XDR algebra. And there's a complicated differential. But importantly, this is identification of vertex algebras. Whereas where the vertex algebra structure on this is just the tensor product vertex algebra structure. Well, the reason being so is because like in all these manipulations, I'm using natural adjunction between GU and GK. So you can see that at the chain level, I really get a non-trivial vertex algebra. My OP is non-zero over here, and it's trivial over here. But we know that in cohomology, this has to have trivial OP. Now, this equality, this chain model manifests the vertex algebra structure on this vector space. And what about the algebra structure? In fact, you can calculate a DJ algebra that manifests the algebra structure on this. I will give you the answer. The answer is, roughly speaking, the universal enveloping algebra of the following algebra. As an algebra, it's just the universal enveloping algebra of one shifted cotangent of G with negative loops. So you can see that they sort of have the same size, and it has a differential, roughly the same differential. But you see that these two, one of them manifests a vertex algebra structure in which these two just totally don't talk to each other. Here, this chain model manifests an algebra structure, but in this case, these two talk to each other because this is really a semi-direct product. So I shift this to degree 1. And here they have a non-trivial commutation relation, whereas here they have a trivial OPE. So in order to find some homotopy between them, somehow you have to use the fact that you have a lambda pairing here. And yeah, this is some stuff like I would like to understand more explicitly, but Unfortunately, I don't know how. Okay. Either way, these are some examples that, and if you have a full machinery of how to turn one-shifted lambda brackets into a full E1 chiral algebra, these are some examples. Then you could check, see if what you starting, if you start with one, and the result should sort of be like this. Okay, the main focus for me is actually in 4 dimensions. So here, everything is in 3 dimensions. So now let's talk about holomorphic topological theory in 4 dimensions. So here, let's write it as C times R times R. Okay, I forgot to talk about the local operators. Let me just quickly mention here. I mean, local operators, again, like you would say it from a chiral E2 algebra. And what we know is that the cohomology of local ops, in this case, will be a 2-shifted Poisson vertex algebra. And this is a very interesting place for playing with these games because the people care about quantizations of these stuff. And one question that's not solved yet is if I have a 2-shift, one of these shifted Poisson vertex algebra, can I actually get quantize this to get a vertex operator algebra? In some cases you can, but it's actually not known in general. And I think one of the important steps is to turn one of this into an actual E2 chiral algebra, which again, I don't know how to. But my focus is going to be line operators. So this is going to be operator supported at a point in C and maybe the entire R over here. So it's going to be supported at a point in C and a point in the first R, and it will occupy the entire second R. So in some sense, if you forget about this just looks like a local stuff in the 3D holomorphic topological theory. Therefore, it should have sort of the same kind of structure as this, except you change algebra into a category. So in particular, you should have a category now. Instead of a multiplication, you say there's a monoidal structure. And instead of OPE, you say there is a chiral or there is a intertwining functor, whatever that means. So the following is actually the full realization Castello is that this setup will lead to spectral braiding and integrability. So that's his insight. And now I'm going to explain to you basically the work of Castello himself and his work with Witten and Yamazaki. And what his idea of constructing these is. And it's very similar to what we just described here. Okay. Can I erase this? Oh, sorry, I should say any questions. Just, please stop me.
Sorry, I'm finding what right now. So what is this work of Castello and others? So again, you're just describing examples of structures that here.
Yes. So what I'm trying to say is that if I look at the line operators in these 4-dimensional holomorphic topological theories, I'll explain that such a category should lead to a spectral braiding. And if you can engineer it well enough, this will lead to quantum R-matrices in 4 dimensions, yes.
So how many supers I'll guarantee
To
what is the
n equal 1, yeah. I think Chern-Simons theory is one of them. And well, my focus is going to be n equal to 2 theories, which has more than enough. Sorry, my focus is going to be 4-dimensional into 2 theories. Kapustin twists. Yes. So they have topological twists in the Donaldson twist, but I will focus on Kapustin's twist. And basically, the story there is actually a lot simpler because there's a geometry behind it. And our construction of all of this is just by staring at this geometry. The geometry of affine Grassmannian, basically. Okay, so
So is it true that this thing globalizes to like manifolds that fiber over curves?
yes, so I think the theories that I talk about, you should be able to define them on transverse homomorphic foliations. So locally of the form sigma times c. So where this is complex, this is topological. Yes. Yeah, thank you for the question. Any other questions?
They have a paper also good definition of application such as the space development structure.
Yeah,
So you don't even need to write it as a product, you just need to
locally is a product.
integrable foliation,
Mm.
integrable fusion.
Yeah.
So if I'm saying correctly, that's the structure of the manifold that you need in order to be able to build
Then we consider proportions or something like that.
I don't know.
So,
That was
certainly.
my question, but I don't think this is known.
Yeah, certainly you could. So for example, even if you look at operator products that expansion, like OPE of local of vertex algebras, it's supposed to come from such kind of 3-point conformal block, which is a cobordism. And but in general, it's hard because if your vertex algebra is not rational, you don't know how to glue these things together. When it's rational, you know how to glue them together, and you can define state spaces in general. But yeah, there is this Atiyah-Siegel formalism for conformal field theory, which you should really define what you assign to any complex curves with punctures or any holomorphic manifolds. But that's certainly beyond the algebraic setting. But yeah, which is what I will work on. But yeah, thanks for the question. Any other? Cool. So yeah, I think I should probably speed up. But basically, now I claim that if I have 2 elements, 2 objects in this category, you should think of them as really point-like in the c times r direction, and they stretch in r direction. Then I should be able to write now, instead of equality of objects, equality of elements in a category, I should be able to write the following morphism. So L1Z is just L1 translated to Z. And then if you just follow this the circle, changing equalities to functors, you expect such a morphism from multiplication this way to multiplication this way. It's understandable because here, what am I doing is that I'm trying to collide 2 things over here, but keeping their separation in Z. So I should be able to just swap. But moreover, this Z should only be defined when away from the origin, because when Z and 0 are both at the origin, then I can't swap. So it's a genuine monoidal category that's not symmetric, but it should have a braiding that's everywhere defined except at the origin. And moreover, the compatibility condition of this braiding with the monoidal structure, we'll say that this thing should satisfy some co-cycle condition, which is just the quantum Yang-Baxter equation. So that's kind of what Kevin realized. Yes.
I'm this stupid listener. So you're doing a line operators in 4-dimensional theory. Right?
Yes.
So it's codimension 3.
Codimension
So it's supposed to be 2 categories, right?
No, it's 1 category.
Like for example, in 3 dimensions, what is such?
So whenever you
sorry, it's
whenever you look at 1-dimensional, so I already erased it, but so k-dimensional defects always have a k-category structure, and then it has, if it's in topological field theory, then the codimension will give you all the multiplication structures. So 1-dimensional defects are 1 categories. 0-dimensional defects are 0 categories, namely vector spaces.
Oh,
So
so
it could be something like an E3 category?
So when you say line operator, it means that you're actually sort of looking at what happens in transversal matrices.
Yes, yes.
So
In fact,
it's something like an E3 category, right?
Almost,
Like an E1
yes.
spiral category.
yes. So if it turns out that this thing is topological, then this is an E3 category, because then you can make this into a sheaf of D modules, and then you can the C of Z has to come from like measuring monodromy around 0. So, but yeah, exactly.
So it's something like an E1 chiral category? No?
Yes, yes. Yeah, I mean, it should be a E1 chiral category.
There are more grading solutions. So that means that it's not E anything.
No, I think it is E1 because the other R gives you E1.
Yes. So
Okay, it's E1.
This-
E1, but that,
Yeah, E1 chiral category.
yes.
it's 1 chiral category, but what am I confused? So, but also have this meromorphic grading.
Yes.
That's the
Compatibility.
That's the compatibility between the chiral structure.
Oh, I see.
Yeah. So in particular, I would like to propose that any E1 chiral category you should be able to write down such a braiding. I don't know how easy that is. But yeah. Okay. So that's the first realization of Kevin and company, and the second one is that if this will be related to dimensional reduction, suppose you can engineer a setup. Maybe you choose some complex curve, and you maybe add some puncture at some vacuum and infinity, and then you can ask, you can take your 4-dimensional theory and do a dimensional reduction along this complex curve. This will give you a 2-dimensional TQFT because you integrate over the complex dimension already. Suppose such a TQFT usually, again, according to cobordism hypothesis, is assigned a category, basically the category boundary conditions. There's a C. Now let's suppose that you can do something interesting to make C to be the same as vect. Then what you can do is that you can take your line operator category. If you insert this line operator at various points on sigma, they will become interface of your 2D TQFT. In particular, it will act on vector spaces. In other words, you'll get a fiber functor to vect. In fact, this fiber functor will be both monoidal and sort of chiral, in the sense that, like, you can put them at different points in sigma, still just tensor product vector spaces. And the C will become a braiding, which is meromorphic dependent away from diagonals of this like that. So and basically this becomes a transfer matrix. This you can use this to construct transfer matrix and the state. This will be an integrable model whose state spaces are given by these, and R will become the Hamiltonian. So basically, this program actually not only tells you that you can engineer integrability from these four-dimensional theories, but also explains the origin of all of these integrable models. In particular, their main kind of playground is that 4D Chern-Simons theory for simple Lie algebra G. You can engineer so that a system that sees vect, and in fact, the sigma will be just P1. And then you put a puncture in infinity. You put some vacuum in infinity. And they show that you can get such a fiber functor. And moreover, they argued, basically based on Drinfeld's uniqueness, that the algebra that controls this fiber functor is Yang. And this R is therefore the universal spectral R matrix of Yangian. So this is a four-dimensional origin of Yangian algebra. Yeah.
So for example, now Yangians have quantum effect because Yangians are kind of additive. You're
Right.
Something
Right.
additive, but quantum effect is multiplicative.
Yes.
How do you know which one it is? I mean, if I look at it, so why is it additive and not multiplicative here? Is it because you're doing this on
Yeah. So yes, local operator on C times R times C. Yeah. If I did it on C star, it'll be quantum affine.
Then C star just no one stops at those.
Right. But so quantum affine doesn't control line operators in the 4D theory. It controls line operator in the dimensionally reduced theory. Yes. Yes. Or 3. No. Yes. Sort of. Yeah. Quantum affine should be 5D on C times C star times R, something like that. And then you dimensional reduce on the C star. You get a sort of a Chern-Simons theory whose gauge group now instead of G's becomes loop of G, and that gives you the quantization of that gives you the.
So here when you're saying this meromorphic grading, you're sad that we talked about it. So it's sort of additive.
Yes, it's additive.
So
Yeah.
for example, when you say that it's meromorphic, it just has poles. So how
Yes.
do you know where the poles are? So
The poles just wherever the 2 points collide. You put them at various points on the complex curve. Yes. Yeah, it's not. There's no Q. Yeah. Yeah. To get Q, you have to go and measure up. You have to look at C times R, and then you impose some condition. You take these to be holomorphic curves, and you say XZ is QZX. This is where the Q come from. All right. So here there's no such.
No, it should be quick. In Yangian, that's all what now. So Yangian's poles are one, two points by H bar by integral multiple of H bar. It shouldn't be equal to H.
Sorry, what do you mean?
I mean, if you have this parameter H bar,
Right.
And I think that the poles of the grading in the Yangian is when if they say two evaluation representations. Then the poles of the grading will be for GLF, for example, will be when the difference of these two parameters is H bar times an integer. So it can't be 0. So 0.
Yeah, it's.
But they also have poles of double.
Unless.
I'm not sure what that means, but I'm just saying that for the Yangian, just you can say that's it's a whole algebra. So the representation, find dimensional representations. it's a monoidal category.
Yeah.
Yeah, it's meromorphic grading, but I'm saying that the poles are not just where the points collide. It's more than that. They collide up to multiple H-bar.
Yeah, well, yes, because when H bar going to 0, this becomes a symmetric monoidal category.
Yes, but I'm saying that, so then I'm kind of repeating my question. So here said that poles are where the points collide, but we see that what point poles are not
Well,
where points collide.
Well, it has something to do with how does H bar come into being in physics. Like H bar is going to be like a deformation parameter. Of course, if you turn off deformation parameter, there's nothing interesting. I don't know if that's a.
The difference between formal deformation.
It's not it.
This is a purely formal.
No, yeah, I mean, okay. Yeah, it exists as an actual.
Yeah, I know, but
Yeah,
this
yeah,
is the formal.
Yeah, this is a
This is just the formal
Yeah,
notation.
this-
H is an element. So I think you don't have that structure.
Yeah.
You know, that you've gone too far.
But of course you can like look at this subalgebra and then try to evaluate H bar. Yeah, but so I guess what I'm saying so far is that
I mean,
natural-
one level down, it's like a difference.
This H bar is like really H bar. What's the physical meaning? The H bar in the Yangian, what is the physical meaning of it?
it's the H bar in the interaction of the
So it's
action.
actually H bar.
Yeah, it's actually H bar.
I mean, it's like one level down, it's like the formal quantum group first.
Yes. Yes. In fact,
You know, Drenfeld Kono versus
Wait, okay, are we doing perturbative field theory?
yeah, perturbative. Everything will be perturbative. Yes. Yeah. Yeah. Thanks. Any other question? Okay. So let me just say that I guess we have 1 more hour left. I need to speed up a bit. Our work is to try to find such a quantum algebra and such a braiding for perturbative Kapustin twist. So our work is to try to find this structure from Kapustin's twist. Of 40 into 2 theories. So let me first tell you very quickly what labels these theories. These theories are labeled by a group and usually a symplectic representation, but I'm going to take it to be of cotangent type. So I can use geometry. And so Kapustin shows that there is a holomorphic topological twist. So I can define this locally on C times R. In fact, I can define this on any complex curve times Riemann surface. So if I look at the situation where V is the adjoint representation, then this enhances to an fourth super Young-Mills theory. So enhance. There's a form of further deformation.
Well, so there's just one. I mean, this Kapustin with the parameters by view.
Yeah, actually. So
this is just one.
A special point of this entire family. Yeah.
It's a special point of the entire family.
I think so. Yes.
Wait, but that family is
So
that family is all of that family is topological.
So I think there is a two. So I think there's two parameters in L and S, and I think when L is equal to 1, S equal to 0, that's the A twist, and when L equal to 0, S equal to 1, that's the B twist, and I think the holomorphic topological twist is kind of the L and S both go to 0 limit or infinity. I don't remember. So in the twist there's two parameters and usually L over S, yes. So I think the holomorphic topological twist should be some sort of like limit where both of them kind of go to 0. I don't remember the details.
That would be wrong. Start both ways.
Yeah, yeah. Uh-huh.
Okay.
Yeah, but right. Actually, yeah, I don't know how to access the entire family of twists from this. But so this theory turns out to be a little easier in some sense than Chern-Simons theory due to geometric quantization, the existence of some geometric quantization. This was first kind of suggested by Kapustin, and later on kind of rigorously defined by Curtis-Williams, and of course, based on the construction of Braverman, Finkelberg, Nakajima. And moreover, the reason we expect to have such a quantum algebra similar to Yang is because perturbatively, this theory is a Chern-Simons theory. So this is some work of physicists Elliot Safronov. Safronov is not fully physicist. It's a physics work where they show that kind of perturbatively, if I only deal with the Lie algebra rather than a gauge group, this is a perturbative gauge theory. This is a sort of a Chern-Simons theory, but for a interesting gauge group, Lie algebra. So I take the Lie algebra of G, semi-direct product with the representation V, shift it to degree 1, and treat this as a graded Lie algebra, and take its cotangent, and that Lie algebra will be the input of this Chern-Simons theory. So in a sense, we expect a similar kind of story, some quantization of Yan's R-matrix, some quantum algebra that deforms the universal enveloping algebra.
Another stupid question of different flavor. Are you planning to have a break at some point?
Oh, I mean, do we plan to have? We can have a break. Yeah, let's have a break. Yeah.
I mean, that's happening now.
Yeah, no.
Whenever
So,
is it?
Whenever you think is best.
give me just maybe 5 minutes. How about 5 minutes and I'll take a break, and then basically, then I can just focus on our results. So the reason I say it's a little easier is because basically Kapustin sort of already argued what this L should be. And his argument roughly is as follows. So what he found is that if you take this theory and just dimensional reduce on sigma, you get a 2D B model. So I'm not going to put this on sigma times C. If I dimensional reduce this on sigma, then I get a 2D B model whose target is rough sort of the moduli space of G bundles on sigma. So boundary conditions are just sheaves on this guy. And if I dimensional reduce it on C, I get a half-twisted conformal field theory whose target is the space of Hitchin moduli space on C and its generalization. So this is the part we'll focus. We'll put line operators and let them act on boundary conditions. And remember, I said that if I have some two-dimensional reduction, I put a bunch of line operators on this, it will act on the boundary conditions. In other words, it will act on sheaves on this big space.
Well, which of those is holomorphic?
So this is holomorphic.
So what is H of C?
Hitchin moduli space.
Means what? Or just, I mean, it doesn't have any, if it doesn't have a holomorphic structure.
Oh, you give it a holomorphic structure and show that it's holomorphic independent. I mean, this is a curve, so yeah. So I mean, Hitchin moduli space, in a priori you need a complex structure to define, but it's a topological field theory. Yeah. So basically, giving line operators, reduce them, you get some line operator, you get interfaces that act. And basically based on this a similar structure in four-dimensional super Yang-Mills theory, he argued that L acts by Heck modification. And so Curtis and Williams basically took this and used the BFN construction to tell us that this category, in the case of pure gauge theory, it's just the category of coherent sheaves, or you say incoherent sheaves on this double quotient space. Or in other words, this is equivariant affine Grassmannian. So here K is formal Laurent series, O is the formal puncture series. And the action by Heck modification roughly comes from a convolution diagram, if I've seen one of those before.
To get this harmonic grading, you also need to test the C star.
No, actually, I can't. If I want to have C star grading, I cannot turn on loop rotation. Loop rotation means that I can't.
Will be honest to grade it.
No, because so if I somehow turn on loop rotation, then I'm not allowed to move the line operator outside it.
But I'm confused because this category I think is graded.
This?
Honest to grade.
This?
Oh, yes.
No, it's not braided. It's not braided.
One is the nearby cycles.
Yeah, this is not D module. Yeah.
No, it's not nearby science. It's the year sheet.
It's
No,
coherent.
exactly.
Yeah.
So I mean, in T-Mods,
So-
the way you do it is there's some nearby cycles. Not available.
Right, but there's also this.
There's another way. Another way to write this category roughly is.
You're right. Yes, so we don't necessarily, but loop rotation acts on this category. So yes, so somehow, right, so you can talk about meromorphic grading, but I understand we can talk about meromorphic grading, but for example, have a C star acting on the category, which is exactly what we're talking here. So you're not considering equivariant objects, you consider just
Objects.
Loop on the category.
Right.
But then it is but then it's kind of multiplicative, right? Which is
No.
So okay, so what I see on this category is that this is a monoidal category.
Yes.
On which there is a C star action.
Yes.
And then, so the grading is meromorphic in the sense that somehow if you take two objects, and if you move both of them or one of them by generic element of C star, then you have an isomorphism between.
Well, if they're both at 0, it doesn't make sense to multiply. So you need to translate first.
No, it is honestly monoidal.
Yeah, it's monoidal, but I have in order to get a braiding, I have to translate in the Z direction.
Yeah, but the translation, what my question is that it's not different.
No, this is actual translation. So what no, there's no such translation indeed. So what I'm going to show is that I'm going to take this again, because I'm only going to consider perturbative theory. I'm going to do everything with a Lie algebra rather than a group. So I'm going to show that there's an algebra representing this category. That algebra has a translation action. Yes.
I'm just saying that, but still, I mean, even if you do that, it's still C star is still C star.
Yeah, C star is C star, but there's also translation. So I'm saying that, like, if I put this thing on a curve, let's say put on C, then we know that this locally this factorization structure on C is trivial. Yeah. So then I can just put a line operator here and ask what happens at various points. And I'm not to do that. In fact, Curtis-Williams did this. So they actually used the monoidal factorization structure to find what they call renormalized R-matrix, which is my understanding is that's the kind of the most singular part of what you want to be C of Z. But yeah, I would like to see if somehow you can like come up with the entire rating. But okay, so let's maybe we can take a break and then I'll say our main results and tell you how we constructed it. So when should I stop?
Stop. Like,
How many more?
or it's when.
Or
4
should
or
I-
5 is when they'll start kicking
Okay.
us out of the room. I think.
I'll try to be quick.
And that's true, actually. There might not be anything after us.
Okay.
So, yeah, keep going until they kick us out or until everyone else leaves. That's scary.
Yeah, we also have the reception.
Ah, that's true.
This you don't want. I tend to get nervous.
Okay.
Yeah, it's great.
I'm not great with like categories of line operators, so I think that at times I get a little lost. Like, a lot of it feels like.
So for example, this example of equivariant iterations on affine Grassmannian.
Yeah.
Well, okay, so finite length only makes sense if you have a T structure. There is a T structure there.
Yeah.
There's a perverse T structure there, such that they don't.
Uh-huh.
But you don't need that to show that K0 is commutative.
No, you don't need, but.
You need these Bayes and Dream thought.
Have some kind of finite.
Sure.
You gotta get finite.
Yeah, you have to show that this factorization structure preserves coherence.
But roughly what happens is that just take K0. And in good cases, this will be a factorization algebra. Okay. And in the cases where it's like regular polynomial, that will guarantee that it's. Does that kind of answer satisfy you?
Yes.
Great. Yeah, thank you. So basically, let me just state my main result and tell you how we. I'm gonna erase this. This is a joint work with Rashid. First one is there exists a quantization of universal enveloping algebra D of T. We call that D here for me is T star of G. The existing part don't require G to be simple, doesn't require G to be anything, doesn't need the algebra. With respect to the co-algebra structure given by Yan's R-matrix, here C is the quadratic Casimir of D, which has a pairing because it's T star of G. And this we know that this defines an Lie algebra structure. I'm gonna call this algebra Yangian of D. I know that Sasha doesn't like this, but for me, a quantization of Yan's R-matrix is Yangian. Moreover, when we show that when G is simple, such a quantization unique if we require to respect two bratings. So this defines a Lie algebra structure on DT. Yeah, and in other words, the Manning triple is just dk is d of O plus d of T. So when the Lie algebra is simple, when G is simple, T star G is never simple. This is the unique quantization. But it's not the unique quantization, it's the unique quantization respecting two gradings, respecting two gradings. And the first one is the loop grading. And the second one is an extra grading where the G star part is in degree 2. So I shift the second one by degree 2, and I have to have H bar in degree -2. And finally, this algebra has time translation operator, which act as Hopf algebra derivation. So use this, I can define sort of this translation operator, which is just e to the zt. You can treat z as a formal variable, or you can evaluate it. And moreover, there exists a meromorphic R matrix such that R of z swaps tensor product one way and the other with a z braiding, and this z has essential singularity. So sort of look like e to the 1 over z. And well, not e to 1 over z, it's e to the something over z. And it's going to become a meromorphic function if you evaluate on smooth modules. Otherwise, it's just a formal series. And this is equality of either functions on smooth modules or formal series. Okay. And plus our satisfied quantum Yang-Baxter equation with spectral parameter.
So, sorry. Just about the whether start with so which theory are we talking about right now?
We're talking about a holomorphic topological Kapustin twist of 14-2 theory.
Oh, which one?
Of gauge theory with gauge group G, Lie algebra G. Sure, but as I said, besides this uniqueness, the rest of these are all true for. You can take a Lie algebra of the form G semi-direct pi v, and this would be the matter theory.
Oh, I see.
So you can take a graded Lie algebra and take D to be the cotangent of that. And the same structure works.
But pure gauge theory for any algebra now.
Mm-hmm.
But you need you still need something like invariant form of the algebra.
Oh, so T star G has an invariant bilinear form.
Oh, so you start with any algebra and take its
Cotangent, yes. This is the statement that sort of like this into two gauge theory look like perturbatively look like a BF theory, or like theory for cotangent.
And then again, what is the statement? There's a quantization. So are you describing this graded, this meromorphically graded monoidal category?
I don't know how to show that this is actually all the structure can come from affine Grassmannian. What I will tell you basically as I go through the construction is how the monoidal structure is related to the.
What is the category?
So there's no category yet. So I guess I said that I'm going to stare at this category and use it to construct this algebra.
Oh, you're saying that you're describing that category
using module of this algebra. Yeah. Sorry, I should. Right. So this is a Hopf algebra, and the Hopf structure will come from the monoidal structure here. Will be very clear, and this braiding will be constructed sort of from the meromorphic. From the chiral structure here. Yes, at 0 and identity. That's why I'm only stating this for the algebras. I don't, again, like I would love to see a full calculation of C from the entire category. I just don't know how.
So just want to understand what is supposed to be the structure, like physics language. So take this full category, not the formal completion of one, but the full category.
Mm-hmm.
Is it actually supposed to be really the category of line operators, or
yes,
in the non-perturbative theory?
Yes. So this full category should be the non-perturbative.
I mean, how can it be that, when you consider formal completion of one, then your category becomes much smaller.
Yes.
So
yeah.
How can it be that the perturbative theory, the category is like much smaller? In terms of size, I feel that doesn't matter whether it gets perturbative or not.
It should, right? There's monopoles that you just can't see. They're not so here line operators are built from kind of multiple copies of identity, and you try to deform it by a Morikaton element. And there might be like a non-perturbative construction of operators that you just can't do it using identity. It's different maybe in 3D. In 3D, what happens is that a local operator actually gets smaller from perturbative sector because like multiple operators sort of kill some generators.
Yeah, if you count the classical form branch, if the quantum and the actual quantum form branch is more or less the same.
Same.
So it's bidirectionally isomorphic. So here, you sort of one categorical level up, and for some reason, they're relatively.
Well, what's the K theory? Well, I don't know what's the relation between K theory. These two, I think they're
Quite small.
quite similar.
I mean, K theory
I'm not
is,
sure.
now have is just K theory of the point with respect to G.
Yes.
It's just go up.
Mm-hmm.
It's up.
Yes. Yeah, I'm not sure. What's a good explanation for this? Yeah. But yeah, thanks for the question. I think I don't know if there's a physical meaning of that.
It's just surprising.
Yeah. Okay, so any question about the statement? So the statement right now seems like it has nothing to do with L hat as I wrote it, but basically what I'll tell you is that I actually constructed this basically by staring at that algebra, that this space. So and I actually so you might ask where H bar is from that picture, and I also explained that. It's kind of stupid, but I don't know how. I don't have a good explanation for it. So
So the quantization, so you have three statements, so these three statements are.
first one, there is such a quantization.
Yes.
And the second one is when G is simple, then this quantization is unique. If it is it's the unique quantization that respect two gradings.
Okay.
And the third one is that there isn't
But
knowledge.
G simple means that you take a simple algebra, because it is with the tangent.
Yes, yes. So then there's no uniqueness statements in general because you can't control cohomology of the algebra, but you can control graded cohomology, and that's kind of what Rashid did.
Or more generally, you cannot just write down this quantization explicitly.
Yeah, this is what I'm gonna do. So I can write down explicit one. I don't know if it's unique. In general, it cannot. I don't know. It's unique. Anyway, so I'll write down this algebra. It's actually very simple. Again, like everything I understand is pretty simple. So I'm gonna stare at this category. I'm gonna actually replace formal groups by Lie algebras. So roughly, you should think of this as like the algebra equivariant sheaves on GK mod G of O. The first step is to define the algebra. And the way I define it is the following. So I stare at this and think, oh, what's sheaf on this? Well, sheaf on this is functions on the linear dual of this, or symmetric algebra of a linear dual of this. And I can think of this as the linear dual of this vector space. If you do formal geometry, then you say that this co-commutative coalgebra is the global section of the dualizing sheaf of this big vector space. And therefore, sheaves are roughly co-modules, and more modules for the dual. And then you can of course show that this is roughly, this is basically the dual of this is identified with G star of T using the residue pairing together with pairing of G and G dual. Great. So that's this part, and then now impose geo equivariance. Well, geo act on this space now, because then there's a left geo module action. This action is given by is a co-derivation for co-commutative coalgebra. So if I take a dual, this acts on this vector space as derivations. So then I can take a smash product. And then yes, I'm just asking for geo equivariant modules for this commutative ring. And of course, you can believe me or you can check that you can just use grading to show that I can restrict everything to the subalgebra. This is basically why. Now, I have to tell you what H bar is, but H bar is this stupid thing where I'm going to pair G and G dual with an H bar. So it turns out that once you introduce this H bar, this parameter actually makes this thing interesting, such that the H bar going to zero limit, you recover your algebra, the universal enveloping algebra. This is actually interesting. One of them is in the Lie algebra, one of them is dual, right? My D.
No, but you're using the same indices. Are they in some sense?
Yeah, that's the dual bases.
So with respect to some Killing form?
With respect to pairing between G and G dual.
Oh.
So my generator should be elements in T star G of T. So I have so roughly XAN, TAN. Huh?
Is there some homological grading?
So physically there is an R charge, and this two come from that charge, but geometrically I don't know where. Yeah. Anyways, so this is algebra, very simple, and you can see explicitly that I'm trying to look at that category. Now let's look at
some G plus G star. So what does it have to do with the previous discussion? So before you had this, so you had a discussion of pure gauge theory for, say, reductive group G. How is that related to this G plus G star?
So what I told you is that basically there's this work of Elias, Safronov, Williams, who shows that perturbatively this Kapustin twist of gauge theory for gauge group G is a BF theory for the cotangent of G. A BF theory, or like a Chern-Simons theory for this Lie algebra. Yes.
And that somehow has to do with the fact that it's only considering this formal completion.
Yes. Yes. Again, this is a perturbative statement. Yeah. Thanks for clarifying. Yes, and I should be more clear about it. So that's the algebra, and now we'll construct monoidal structure. So yes, we're gonna describe this as a Hopf algebra. So I define the algebra. Now I define Hopf structure. The definition of Hopf structure will use the following: that I will take my G of K, and I know that I can always decompose into this as two subalgebras. Roughly speaking, my fiber functor will be the following. So my L hat is roughly a double quotient of G of O, G of K by G of O. Now I can consider it, of course, act on this sheaves on this space by, again, convolution. But if you look at this decomposition, this tells you that, roughly speaking, sheaves on this space is vect. So by looking at such a decomposition, I can build a fiber functor. Now let's be more explicit about how do we write it down. So from now on, we'll replace this affine Grassmannian, the formal completion, with just the space itself. And then I can rewrite the monoidal the convolution structure, which roughly becomes the following.
From the way you wrote it, it doesn't, but it also looks like the formal completion of the trivial bundle on 1G of P1.
Formal completion, yes. Actually, this is the formal completion at a specific.
Well, at a trivial bundle.
No, not
G-
trivial. Trivial, you would have this,
Ah,
right? If it's trivial bundle, you will have GT inverse.
I
It's
see.
precisely this T inverse. Yes, thanks for the question. This is actually the formal completion at over P1 over bound G of a very specific sheaf of Lie algebras. I mean, this is defining a sheaf of Lie algebra. In fact, you can interpret this as kind of a vacuum. Physically, you interpret this as a vacuum and infinity, and mathematically, you interpret this as like a specific G bundle on P1 that you are looking at its formal completion, and because there's no moduli, you get vector space, and therefore you get fiber functions. Great. So yeah, that's precisely it. And basically, if you just stare at what these two maps trying to do, this gives you a coproduct on the symmetric algebra, basically dual to Baker-Campbell-Hausdorff, because this is just multiplication of this. This gives you a coproduct on the universal enveloping algebra, basically by telling you that the action of GO on the left here comes from a combination of GO and a combination here. But this is the interesting part. So roughly speaking, delta H bar will look like x tensor 1 plus phi prime tensor x prime, where phi prime is our functions on this that tells you what happens when you take an element and pass this element through. Right? Because when you take this pullback, this action, this GO will act on both of them. And the action on the first one is the standard regular action. When you want to act on the second one, you should multiply them kind of, so we're going to braid them across each other and then multiply to the second. And this phi prime tells you how it does it. And geometrically, this just comes from this fiber. So claim is that these glue to a well-defined co-commutative co-product. Great. And then I will. So I define them separately on G of O and on the symmetric algebra. You just need to show that they satisfy the correct commutation relation because it's sort of defined as a smash product. Right. And finally, you can define antipode and equivalent. I won't do it here.
But you're supposed to have this meromorphic grading. So
No, not yet. So I'm just defining Hopf structure. But
it's co-commutative.
It's not co-commutative. I mean, this is Baker-Campbell-Hausdorff. This algebra is far from co.
It's co-commutative.
No, I didn't write co-commutative.
In the claim, you did well-defined co-commutative claim.
Oh yeah, sorry. Yeah. Co-associative. Sorry, that's what I meant. Right. So, yeah, this is not co-commutative because like this is like the dual of the Baker-Campbell-Hausdorff, so it cannot be co-commutative. And you can see it from here too.
No, that's fine.
Right.
We don't want it to.
Yes. Great. Okay. So this is the construction of the Hopf structure. And before I go to the construction of the meromorphic grading, I just have some quick comments. Yeah, the fiber functor. No, it's action on this.
Oh, just
So this thing has a convolution action by GK mod GO mod GO. And then if you're already splitting, this category is trivial. This is actually computing cohomology of a sheaf of the algebra. And sort of this is the tangent space of that.
So what is the fiber functor in these terms?
So the fiber functor in these terms is given by the action of this category on And then this I interpret as some G bundle or some Lie algebra, specific Lie algebra bundle on P1 on which I'm taking its tangent space. And the tangent space is trivial, so this is just fact. Yeah. So I guess that's the first comment. The second comment is that, okay, you see that here, all I need is actually a Lie algebra and a splitting to two Lie subalgebras. So this construction is pretty general. You can apply it for any Lie algebra and the splitting. This give you a fiber functor for the convolution monoidal structure. Yeah, it's just so okay. The relation between this splitting and Manning triple is the following. So from such a splitting, I can get a Manning triple inside T star G of K by taking conormal of these two.
No, I was saying that this I mean, you have a Manning triple inside G of K itself, right?
Yeah, but I'm not using that bialgebra structure. I'm using the bialgebra structure here. Actually, that's related to the second. So
Okay, so what is the Manning triple of T star G of K?
from this is just be T star G of O plus T inverse T star G T inverse.
Yes. And so okay, so that's
This is the conormals. So actually, again, because all I need is a complementary subalgebra of G of O, I actually have a lot of them, right? So it turns out that to find such a G of O, to find such a splitting of Lie algebra, all I need is a R matrix. Classical. So here I'm assuming G is simple. So for every classical generalized R matrix, an element of the form so if I have such a tensor whose only singular part is the Young's R matrix that satisfies generalized Young-Back's equation, then this expanding over one of the T1s and then looking at its coefficients, I can define a Lie subalgebra complementing to G of O. So from such an R, you can define a Lie algebra that's complementary to G of O inside G of K, and you can apply for all these constructions work.
so this G now what used to be T star G?
No. G now is still G. I'm just saying that a simple G, I can actually find a lot of different splittings from classical generalized R matrices. This by itself is not a Manning triple.
G itself,
For G.
Do you stop at conormals?
Yes. So the corresponding. So here, this is not a Manning triple, because G of R might not be equal to G of R perp. This has something to do with this R being generalized, not actual R matrix. But you can take any of this and just take its conormal. That's always going to be a Manning triple. And basically, the statement is that if you have a generalized R matrix, you can always do a skew symmetrization into T star G and get an honest matrix. And our construction actually give a quantization for this. And finally, of course, if you choose it, so this also has a geometric meaning. Beilinson and Bellavin and Drinfeld tells us that this is again a sheaf of Lie algebra over some curve of low genus less than equal to 1. So you can think again, the monoidal structure come from the same kind of picture. And you can think of this as some like G bundles on some formal completion of G bundles on some curve. Curve is encoded in this R. And finally, all these different splittings should give me the same category, because my starting point is the affine Grassmannian. It doesn't require me to have a splitting. So it turns out that for different R's, the resulting Hopf algebra is twist equivalent. So there is a quantum twist, like in the sense of Drinfeld, in the sense that there is an element in that satisfies some co-cycle condition that kind of braid one coproduct into another.
It's
About,
right,
they have the same tensor category, but two different fiber functions.
Yes.
Different algebras. Not isomorphic, but
But
it's equivalent.
They're equivalent.
That's the equivalent.
That's the equivalent.
I see. So rapid conjugation.
Yes, conjugation, yeah. Great. So do I still have time? 10 minutes, great. So I'm gonna quickly sketch to you how I constructed this R. Hopefully it will make sense.
Before I said you can set this fiber functor, which.
I actually don't know the geometric meaning. Yeah.
So choice of this whole function corresponds to choice of fiber functor.
Right.
So you're saying that for each such R, you can choose a fiber functor.
Yes.
And see what it is.
Oh, it's
Oh,
given.
you wrote it over there. So,
Yeah.
Yeah, but the trick is find some curve, like some Lie algebra bundle.
Curve, I know. Curve.
With no
Like a
moduli.
curve.
Mhm.
And find some Lie algebra bundle with no endomorphisms.
Yes.
The
With
algebra bundle.
And so the formal neighborhood of that is just a point. So like
So
a
you
isolated
can say it again. So you find the curve and then you see the algebra bundle on the curve.
Yeah, which is an isolated point with the modular space.
yes.
Okay.
And then act on that.
Modular space of what?
Modulus.
Space of
Two bundles, it's Lie algebra bundles.
the algebra. Okay, yes.
Yeah, and then act on that, and then gives you the fiber. The action, because the thing you're acting on is that.
But how can it be how can it get an isolated point? Modular space of points.
Well, if it's a non-trivial bundle, so.
Yeah.
By isolated point, I mean that the cohomology with the adjunct
Is trivial.
is
Yeah.
trivial.
But that's the tangent space inside bound G.
So just-
Well,
I guess the assertion is you can find such.
well, I thought there was some Riemann-Roth theorem prevents it.
Sorry, what do you?
I think these are might not be smooth.
No, but on
So-
one, like the cohomology of O minus one is.
Yeah, so you can think of this as like a it's a Lie algebra bundle on a
But
nodal curve.
I mean, the algebra is what? The algebra is semi-simple or what? If the algebra is semi-simple, then I mean, if I have a G bundle, I can consider its bundle, but the morphism says degree zero. So we're.
No,
Well,
I think you maybe take like.
So what I'm
Well, I think it's G plus G star.
Yeah.
so what I
Maybe your quotient take by the.
so
Trace those things or something.
so decomposing GK into G of O plus this is giving you a sheaf of Lie algebra over P1. This is what this Lie algebra is on the formal puncture disk. This is the Lie algebra on the formal disk. This is what it is on the away from.
Actually, some particular bundle.
Yeah.
Well, yeah, can you say what the bundle is?
Sorry, what I mean, this is the bundle, right? Like I'm saying that I'm using a check description of the bundle. This is a over B star, it's G of K. Over D is G tensor D, and over C over the complement of this point is G tensor T inverse CT inverse. The gluing is these two embeddings.
So that's the trivial bundle.
No, because of the T inverse. If there was no T inverse,
Oh,
the T inverse makes it non-trivial.
so the gluing is just multiply either T or T inverse.
Yeah.
Right.
And so that somehow corresponds to O minus one.
I see, so it's not the bundle from the morphism of any sheet bundle, of any principal. This never happened because you get the bundle from the morphism of principal sheet bundle doesn't degree zero.
No, but it's a principal Lie algebra. I think that's the issue. There's no global.
What is the principal?
This is a sheaf of the algebra,
Oh, just for the
formal group.
That's.
Yeah. Yeah, thanks. That's yeah, that's what. In the end, this is describing in check complex a sheaf of the algebras. that has trivial moduli. Okay, so now I'm going to describe how to construct R of Z. It turns out that to construct R of Z, it's very convenient to actually show that. So here I defined a coproduct. Now I'm going to claim that this algebra also has a sort of a meromorphic coproduct. The infinite series of the inverse. And I'll again sketch this definition of this coproduct using the factorization structure of the affine Grassmannian. So what did we do? Well, we used, when we define delta H bar, for example, over G star T, we use the fact that this thing is the linear dual of the universal enveloping algebra, right? To define the coproduct over there due to Baker-Campbell-Hausdorff. Now, on the other hand, this thing is also the linear dual of the Affine-Kac-Moody at level 0. So this thing has an intertwining operator, and this delta Z defined on this is just that intertwining operator. So delta Z F A tensor B is defined to be F Y A Z. This is how it's defined on this part. And now we'll define this coproduct separately on the universal enveloping algebra part. On this universal enveloping algebra is actually just the translation of not that coproduct, but the symmetric coproduct. So in fact, you see that the coproduct on this piece and this piece are actually disjoint. This feature was very similar to the previous three-dimensional holomorphic topological theory. If you recall, I was computing the endomorphism of the vacuum module. And I showed that in one presentation, it looked like the symmetric algebra and the XDR algebra has a non-trivial relation. In another presentation, their coproduct, their intertwining operator just completely don't talk to each other. Here, same thing happens. There, I'm using the monoidal structure, and then this coproduct uses essentially the interaction between GT and this part. Here, I'm defining a coproduct in which these two are totally separate. And again, the claim is that they glue into a weakly co-associative and co-commutative coproduct. In fact, these words are literally the linear dual of what is true on vertex algebras. In particular, basically, what I'm defining here is that the linear dual, I'm really just saying that the linear dual of this can be identified as a vertex algebra with this times the symmetric algebra of T inverse GT inverse. Start. So the symmetric product here is due to the symmetric coproduct here. The interesting OPE here is due to this interesting coproduct here. So now I define this delta Z, and it turns out that to construct this R, we just need to construct a twist from this delta H bar to delta Z. So the next statement is that there exists a twist, well, we'll call it Rs of Z, such that Rs of Z tells Z tensor 1 delta H bar. So remember, this is the kind of a complicated coproduct from the monoidal structure. I claim that I can find a tensor that satisfies co-cycle condition that just convert this coproduct into this coproduct. So I think if you believe this is true, let me then just construct the full R matrix, and then if we have time, I will tell you how this RS is constructed. But if you believe in this, then you see that okay, this thing is already co-commutative, weakly co-commutative. In particular, it satisfies this. So in particular, you can think of this as I'm braiding this into a coproduct whose braiding is identity. Then I can just use this to show that now I can braid this back. You will find something. Now you'll see that you just need to multiply it back. So the full R matrix is this just multiplication. So basically, once you construct this, you construct the full R matrix. And this is very interesting, right? Like if you look at this and look at how we constructed this monoidal structure, this meromorphic braiding, this is saying that this is computing L1 of Z star L2 precisely. This RSC tells you that this is equal to something else, and this something else sort of look like is trying to be intertwining operator. And intertwining operators satisfy some co-commutativity property, and then you can then braid it back into this is trying to be L2 star L1. Great. So that's the picture we have. I don't know how RSZ arrives. It's sort of an algebraic thing. I think I'm running out of time, so I'm not going to maybe talk too much about it. So this is just an algebraic thing we found by looking at the relation between intertwining operator and multiplication. And it's just so miraculously that it can convert this coproduct into this coproduct. I don't know what this means, but I understand how this arises from the geometry of equivariant affine Grassmannian. So I think I'll just stop with that.
What is the statement? Statement is that there is a so that what?
So that I can twist this shifted interesting coproduct into this co-commutative coproduct.
At the expense of what?
At the expense of some poles.
Also, this also has poles.
Yeah, this RSZ. So I can write down the RSZ. It's a closed form. Here, so XA is a set of basis, and TA is its dual basis.
But does it mean that the square of the gradient is 1?
No. Well, this thing doesn't square to 1.
But the square of the gradient is 1 or not is categorical. Like it doesn't depend on how you
Yeah.
right. It's an algebra.
Right.
I think that this thing is at least equivalent to a commutative product.
So yeah, I'm saying that this thing is twist equivalent to a co-commutative, weakly co-commutative.
Commutative product of the category, then the gradient square of the gradient is 1. So that is.
Oh, maybe.
Square of the gradient is something which doesn't depend on the.
Yeah, well, I guess yes. It's probably true. I guess in a way, you mean like yeah. I mean, sure. Yeah, is you can just.
I don't think you need. Well, for the animators.
Yeah.
So it's a strange thing. So it's a meromorphic gradient. So it has poles, but the square doesn't.
Yes. Yeah, because it actually also has a co-commutative thing which has poles. So this one doesn't have pole, but it has a braiding that has pole. This one has pole, but it doesn't. It has a braiding that's identity.
But that is something that you should be able to see from primary, so that you don't need this writing those algorithms. It should deal with this if it's about biggest sheaves of the formula because of one and then my Grassmannian, that this is a category which has this meromorphic rating where's the one. If this
Yeah,
is,
I guess.
if this is straightforward.
Okay. I mean, yeah, I would love to see if like how straightforward this can be done. I mean, it took us a while to figure out how to write. Yeah, actually, so I'm gonna sketch. I think I kind of told you about this, but I'm gonna sketch what's the relation between delta z and affine Grassmannian, and it's given by the following. Write it here, and then I'll be done. So the definition of delta z relies on the fact that the linear dual of this is this vertex algebra, which is a tensor product to vertex algebras. Now I'm going to derive this vertex algebra. So the way I derive this is the following. Let's look at GK double quotient G of O. And then I do a convolution, I do a pullback diagram. So both of them are like quotienting out by G of O. And if you look at what this pullback diagram should be, what you should put here is G of O times GK mod G of O. Right. So these are both projections, and one of them is projection, another is action. And this is the standard convolution diagram. Sorry, pullback diagram. So now let's take the dualizing sheaf of this guy. I can perform a push forward and a pullback. Right. The claim is that this is a co-commutative. This is a co-commutative half algebra over here. This is precisely a ring of functions on G of O. This is trying to say that the co-modules of this is a co-commutative half algebra. Co-modules for this are precisely sheaves on this, just standard the construction. Now, if I ask what's the global section of this sheaf, this is going to be a vertex algebra because everything is factorizable. Now, what I'm doing push forward and pull back. So using a junction, I can instead do pull back, push forward. So this thing is the same as global section. If I first pull back omega and then push forward on x onto GK mod G. But since I'm taking global section, I might as well just take global section over here. And if you think about what this pullback is precisely the structure sheaf of G of O, answer the dualizing sheaf here. If I take global section, I mean, these two things just take global section separately. So this becomes structure functions on G of O, answer with the global section of the dualizing sheaf over this formal affine Grassmannian, which is precisely the vacuum module at levels. So what happens is that what this is really trying to say is that this thing has a vertex algebra structure as well as a co-algebra structure. Co-modules for this thing should have a meromorphic tensor category because I have an intertwining operator. So again, like this delta z, I don't know for any vertex algebras, for any factorization space with a nice forgetful functor. So here I have some nice functors to vect, and that's what allow me to extract this. I think so the same thing. I think I was trying to ask you about this too. So I can ask for what's sheaves on this. And claim that sheaves on this can be identified with co-modules on this, right? And then there's an intertwining operator map which is a map of co-modules. So I can take two co-modules and push along this map. This is a vertex algebra structure. And I'm just taking the dual of that to make it fancier. Like, But it might not have a coalgebra structure. This is like, this is a vertex algebra with a compatible coalgebra. Yeah,
To build these kinds of things.
yeah, yeah.
The exact structure that you need is a least star algebra. I mean, here the least star algebra is just D times D.
Yeah. Mhm.
You can do this for a general least star algebra.
Here's in G itself.
No, no, well. I mean,
Yeah, well.
It's started at the least star.
Right.
It's like a D.
Yes.
That's, I think for an arbitrary.
T does the T.
Yes.
Okay.
But I think this kind of thing should work for any least star algebra.
Right. So this again, like I guess I'll stop here and just say like this is just an example that we worked out, kind of comes from affine Grassmannian. Also, this pretty pictures that I mean this a new solution of quantum Yang-Baxter equation. I think like a lot of these pictures tells me that something general should be true, that you should be able to start with a chiral algebra, the chiral monoidal category, maybe with some nice monoidal functor, and extract monoidal fiber functor and extract some R matrix out of it. So yeah, I'll just stop here.